Hello, my name is Dave. Welcome back to my YouTube channel. In this video, I'll do the review for Chapter 9, Proof by Mathematical Induction from Mathematics Extension 1. In this chapter, it mainly involves two types of questions. The first one is about series. So we have to prove a series from one side to a function from the other side. The second one is we have to prove by a series is divisible by an integer number. For example, a series divisible by 3, divisible by 5, depends on the question. In our answer, it have to cover 3 steps. The first one is usually we choose the smallest number to prove the statement is true. For example, n equal to 0, n equal to 1, depends on the question. The second step is we assuming when n equal to k, the statement is true. Based on this assumption, we go to the next step. We have to prove when n equal to k plus 1, the statement is true. If in the third step, the statement is true, then we can conclude that by mathematical induction, the statement is true. Okay? If we show the steps on the number line, it will look like this. Here's the first step. Here, first step is when n equal to a number. Usually this number will based on the condition. Usually we choose the smallest number. Okay, when this one, we have to prove the statement is true. Then we assuming n equal to k, the statement is true. So here is the assumption. Okay, based on this assumption, we have to prove the statement one step further to n equal to k plus 1. One step further. So if we can prove that the statement is true from these 3 steps, then we can conclude that by mathematical induction, the statement is true. Okay, let's go to have a look at the question here. The first question I chose for this chapter is about a series. So we want to prove the series from one side to a function to the other side. Okay. So here is the condition for n. N is the integer for all the integers greater than or equal to 1. Okay? So let's go to the first step. We choose the smallest number when n equal to 1. Okay, the first step, when n equal to 1, the left-hand side of the statement is equal to, we submit the n equal to 1 to here. We have 1 over 3 times 1 minus 2. And then times 3 times 1 plus 1 equal to 1 over 3 minus 2 is 1. So here 3 times 1 plus 1 is 4. So here would be 1 times 4, just 1 4. Okay? So the right hand side would be 1 over 3 times 1 plus 1 equal to 1 4. Then the left hand side equal to the right hand side. The statement is true. Okay? Okay, the second step. We assume when n equal to k, the statement is true. The statement is true. Such that we have here we can just copy this equation. So 1 on 4 plus 1 on 28 plus 1 on 70, etc. to 1 on 3k minus 2 times 3k plus 1 equal to k over 3k plus 1. Remember we use k over here, not n, okay? Okay, let's go to the next step. Third step. We're assuming the statement is true when n equal to k, then the next step is when n equal to k plus 1. So we have to prove the statement is true one step further to k plus 1. Since usually the right hand side is simple, then we get the right hand side first when k equal to 1, when n equal to k plus 1. So the right hand side equal to k plus 1 over 3 and then k plus 1 equal to k plus 1 over 3k plus 4. Okay, so here is from the right hand side. We want to prove the left hand side when n equal to k plus 1. Get the same to the right hand side, right? Okay, let's have a look at the left hand side. Okay, left hand side equal to 1 on 8, or 1 on 4, plus 1 on 28, plus 1 on 70, plus and 2, 3k minus 2, 3k plus 1. Here's the second last term, and then plus 1 over 3k plus 1 minus 2 times 3k plus 1 and then plus 1. Here's the second last term. Here's the last term. Okay? From the first k term, so here is the first k term, is exactly to this one. Right? Then we can use this one to replace the first k term of the left hand side. 2k over 3k plus 1 and then plus the last term. So here we have to simplify the last term. So 3k plus 3 minus 2 is 3k plus 1. And then times 3k plus 3 plus 1 is 3k plus 4. Okay? Then we can make the common denominator of 3k plus 1 and 3k plus 4. 3k plus 1 times 3k plus 4. So for this term, we have to times 3k plus 4 on the both sides. So k times 3k plus 4. And then plus 1, this one from here. Okay? Then we can expand here with 3k squared plus 4k plus 1. And then over 3k plus 1 times 3k plus 4. So what we are looking for from the left hand side, we try to get the left hand side getting close to the right hand side, right? So from the right hand side, we have 3k plus 1 in the denominator. We have 3k plus 4, 3k plus 4, 3k plus 4. Then we try to eliminate, take the 3k plus 1 away, right? Then we can factorize the numerator from here. Of 3, 4, 1 is 3, 1, 1, 1. So 3 plus 1 is 4, right? So 3k plus 1 times k plus 1. So we have 3k plus 1 times k plus 1 over 3k plus 1 times 3k plus 4. Then we can eliminate the 3k plus 1 over here, right? So you get k plus 1 over 3k plus 4 equal to k plus 1 over 3k plus 4, exactly equal to the right hand side. Equal to the right hand side. Then from the first step, we have proved the statement is true. In the second step, we are assuming when n equal to k, the statement is true. In the last step, based on the second assumption, based on the assumption from the second step, we still prove the statement is true for n equal to k plus 1, right? Then we can conclude that hence by mathematical induction, the statement is true. Is true for all integers n greater than or equal to 1. Okay? When we finish these 3 steps, making a short conclusion, answering the question. Okay? Here's the first question. Okay, let's go to the second question. The second question is, proof by induction that 7 to the power of n plus 6 to the power of n is divisible by 13 for all odd positive number n. So we are looking for n only odd positive integers. Okay, so which means n is starting from 1 to 3, 5, etc. Okay, so the first step, we choose the easy number when n equal to 1 to test this term. Okay, 7 to the power of 1 plus 6 to the power of 1 is 13, which is divisible by 13. Okay, second step, we assume n equal to k, 7 to the power of k plus 6 to the power of k is divisible by 13 as well. Oh. Divisible by 13, such that we have 7 to the power of k plus 6 to the power of k equal to 13m when m is an integer. In the third step, when n equal to k plus 2, it's k plus 2, not k plus 1, because the difference for each n is 2, okay, for odd number only. So we have k to the power of k, 7 to the power of k plus 2 plus 6 to the power of k plus 2. Then we have to, based on this assumption, to prove 7 to the power of k plus 2 plus 6 to the power of k plus 2 still divisible by 13. Okay, then we can simplify this one, equal to 7 to the power of 2 times 7 to the power of k plus 6 to the power of 2 times 6 to the power of k would be 49 times 7 to the power of k plus 36 times 6 to the power of k. Since this 49 can break down into 36 plus 13, right? Then we can combine this 36 with this 36, right? Then we still have 113 times k times 7 to the power of k. Then the next step would be, we break down this 49 to 36 plus 13 times 7 to the power of k plus 36 to the power of 36 times 6 to the power of k equal to, then we can combine the 36. You have 36 and then 7 to the power of k plus 6 to the power of k, and then we still have 113 times 7 to the power of k. Here, 7 to the power of k plus 6 to the power of k is exactly this one, 13m, right? Then we can replace this term with 13m, equal to 36 times 13m plus 13 times 7 to the power of k. Then we still have 113 as a common denominator, right? Okay, keep factorize the 13 times 36m plus 7 to the power of k. We make it equal to 13 times n, where n equal to 36m plus 7 to the power of k is an integer. Okay, so this one 13m, so 13n is divisible by 13 as well. Okay, so on these three steps, we all prove 7 to the power of n plus 6 to the power of n is all divisible by 13 for all the odd positive number, right? Then we can make a conclusion. Hence, by mathematical induction, seven to the power of n plus 6 to the power of n is divisible by 13 for all the odd positive number. And okay. Yes, that'll be all for the chapter 9 proof by mathematical induction review. In the next video, I'll do the chapter 10 factors in 2 dimensions review. Hopefully my videos could help you to have a much better preparation for your HSC exam. If you like my videos, please give it a like and subscribe my YouTube channel over here. I'll see you in the next video. Bye bye.